Okay, so our lesson for today is the intro, part of the intro. Actually, modules 1 and 2 are still introductory in nature in terms of uh, the principles, the concepts that is being included in this particular module or that are included in these modules. There are portions which are review of the lesson in Chem 1 and even your lesson in FEChem, a little on FEChem under the introduction of kinetics. So we will now review them and at the same time introduce new concepts regarding chemical reaction engineering. So I'm sure you can see my screen already. Please just let me know if my slides are not transitioning later. So module 1 is about fundamentals of reaction kinetics. So just like the way it's presented in our reference book by Octave Levenspiel, when we speak of a particular chemical process or a typical chemical process, we are actually looking into three, shall I say, major steps. So the first and the last steps are all physical treatment steps, and actually these are being discussed in your unit operations. Most of these are unit operations and unit processes, but the very heart of the chemical process is really in the chemical treatment steps, where our raw material are being converted into desired product or desired products. So the reason for this first block in here, the first physical treatment step, is for raw material to be freed of contaminants or other things other than those chemical species that are needed in the chemical treatment steps. So as discussed in your book by Octave Levenspiel, these raw materials need to undergo a number of physical treatment steps to make them ready or to put them into the form
Miss,
that they
excuse
can.
me,
Yes.
wala ga mo bang slide miss?
Anong makita niyo sa bunga slide?
Module 1 pa lang.
Oh,
Module 1 fundamentals.
oh my. Sige, sige. Thank you. Sige. So just enlarge the slide in here. Can you see the slide if it's not being projected?
Yes, miss.
Okay, thank you. So where was I? So the physical treatment step, the first physical treatment step was really designed to render your raw materials ready for reaction. So they are put into the form where they can be reacted. Now, this physically treated raw material then goes to the reactor, the very heart of the process where they are reacted to form the desired product or product. So before reaction, it has to go first the elimination of the contaminants and other species that are not needed in the chemical treatment step. Then the last part, wherein we have another set of physical treatment steps, is for our product or our desired product to be separated from other byproducts, or it's the final purification step. So the products of the reaction in the middle or in the second step undergo further physical steps like separation and purification in order for it to obtain, for us to obtain the final desired product. So the very heart of any chemical process that converts a set of raw material or a raw material to the desired product or products is the chemical treatment steps. And that is why, as mentioned by the author of our reference book, that sets us apart, or that sets the chemical engineering profession apart from other fields of engineering. It's because without this chemical treatment step, the raw material or materials cannot be converted into other forms of products, desirable materials, that is. So we can learn unit operations, but without the heart of the process, which is the chemical treatment steps, they are actually, if you're going to ask my own opinion, they are, shall I say, rendered not useful, because the primary purpose actually of the unit operations processes is for the separation of substances from other substances, or for the accounting of the materials that goes in and out of a particular equipment, accounting in terms of the mass and the energies associated with the steps or with the processes. So that's the very reason why chemical reaction engineering is very important. If we're going to simplify this form in here, as illustrated in our reference book for a typical process, this is it. So you have your reactor in the middle and you have separators in the beginning and then the last part of your typical process. Okay. Now, what are needed in chemical reactor design? So chemical reaction engineering will not be engineering without the design parameters. So there has to be the design. So what do we design? So we design the reactor that will facilitate a particular chemical treatment step or several chemical treatment steps. So if this is our reactor, these are the vast field of knowledge that is needed. That way we can appropriately or optimize the operation of a particular reactor. So we need to know heat transfer. That is why you already know heat transfer by now. Same thing with mass transfer. Of course, you know already your fluid mechanics because that was discussed in your transport processes. And you have your thermodynamics before this, and you have your economy already taken. And this is it. So the first part of chemical reaction engineering, as discussed to you yesterday, is about the kinetics of reaction. So that's reaction kinetics. The second part is where we go into design. All of this information are needed. That way we come up with a reactor that will not just simply provide us or produce the product or products that we want, but will have an optimized operation. Optimize at the same time sustainable operation. So not just for the mere fact that it's going to produce something, but of course we have to consider other factors than that. Okay, now let me go down to the next. So how do we describe then chemical reaction engineering? That's your course. This is not kinetics only, but this is chemical reaction engineering, or CRE for short. So CRE deals with chemical reactive systems of engineering significance. So take note of the term significance. So they're just not there because they are to react something and produce something, but that something has to be of importance or significance. Now, chemical engineering can also be defined as the discipline that quantifies the interaction of transport phenomena and reaction kinetics in relating reactor performance to operating conditions and feed variables. Now, relating reactor performance to varied conditions, operating conditions, and feed variables is discussed uh, at the latter part of the course. Okay, it's part of the reactor design. So chemical reaction engineering is that engineering activity that is concerned with the exploitation. So this is how it is defined by our textbook. Of chemical reactions on a commercial scale with the goal of successfully designing and operating chemical reactors. So we need to not only know the kinetics, and that's how fast a chemical reaction will proceed, and how it is dependent on operating variables, but we need as well to design the reactor that will facilitate such reaction. Now, why chemical reaction engineering? So this particular part of the slide tells of the significance of chemical reaction engineering. Why study it? So chemical reaction engineering is needed in the development of new and in the improvement of existing technologies. So either we develop something new, totally new, something novel, not existing before, or we improve something that has been made already. So how do we accomplish this development of new technologies or improvement of existing technologies? So we search for alternative processes to replace the old ones. So we look for more economical, more environment friendly, more, shall I say, equipment friendly in the sense that your equipment will have long life processes to replace the old ones, or either we find new routes to make a product from different feedstock. So we try to find new raw material for a particular end product. We find new routes or new ways of finding new materials from different feedstocks. Then very important as well is the role of CRE in reducing, if not eliminating, unwanted byproducts. It's not just we want to produce the product or the products, but we want to eliminate the byproducts, because the more byproducts we produce in a particular chemical treatment step, the more unit processes we need to separate them from the desired product that we want, or the desired products we want. So as much as possible, we want to eliminate the formation of these unwanted byproducts. And this one, the last bullet that I have written in this slide, is taken from the exact words of the author of our reference book, Octave Levenspiel. So CRE perhaps sets you, chemical engineering or chemical engineers, apart as a distinct branch of the engineering profession. So without CRE, you cannot be called a chemical engineer, because there's no chemical treatment step that will be processed or that will be designed to facilitate the or to make the desired material, whatever that material may be. So that's the thing that sets you apart from the other fields of engineering. That's chemical reaction engineering. Now, in terms of expectation, what do you expect to learn in this subject? Of course, you have in mind that you will be learning kinetics, that you will be learning how to design reactors. So in here in CLE, we will develop a general methodology. So it's general in the sense that a different chemical system will have a different take, a different manner in which it is to be approached to in terms of how the required information in that particular system is sought. So that is why the term is a general methodology. We will develop this general methodology useful in approaching a variety of systems. So we will limit our systems here into chemical systems, because biochemical and biological systems are being discussed in your biochemical engineering come next year in your first semester. So although in part you will have an idea of what's enzymatic growth, what is microbial growth, this will be discussed in detail in your biochemical engineering. So our concern is the chemical systems in here. So example of those chemical system is, of course, the usual chemical production and even pollution abatement. Okay, so that's what you should be expecting to learn here. Now, these are the two things, the core things that you will be learning here. First part is chemical kinetics, how fast a reaction proceeds, how fast a product is produced, how fast is a reactant being consumed, what are the effects of temperature and pressure to these rates that I have mentioned. So that's under chemical kinetics. How do we interpret data? That way we can make use of this data in designing the reactor that will facilitate a given reaction. So that's also part of kinetics. Then the second part is chemical reactor design. So it's only two. These are the two core ideas that you will be dealing with or studying in detail with in this particular course. Now, specifically, chemical reaction engineering has these principal functions. So we have laid down already expectations. So what are the chemical functions now of this course or this vast body of knowledge? So number one, establishing the chemical mechanism of reaction. Now, when you speak of establishing the chemical mechanism of reaction, this actually requires experience. because now no one without the experience of not having exposed to reactive system will know the series of steps, the series of chemical treatment steps that a particular set of raw material or chemical species will need to undergo so that the product or products can be produced. So it takes a lot of experience to know this chemical mechanism. Or shall I say, you should know the first step or the first reaction. After this first reaction, what happens is another set of reaction that will convert the product of the first into another set of products. Then that set of products will be reacted again with another set of species or a species to produce another set of products, and so on and so forth until you reach the final stage wherein you already have your desired material or product. So that has something to do with establishing the chemical mechanism of reaction. Mechanism meaning the series of steps that your chemical species or species has to undergo. That way it's converted to the final desired product. Okay. Now, in chemical reaction engineering, we also collect experimental data. So this experimental data is being collected. That way we can come up with the rate law or the rate equation that will best explain the behavior of your species given the condition in which it was allowed to react with another or allowed to decompose. If it's just a single species, then it will just decompose. Okay, so we are needing or we continue to need chemical reaction engineering in any field because of this collection of experimental data. Even in other bodies of knowledge, it's not only actually chemical reaction engineering that does this. Even statistics need experimental data, whatever is that experiment may be. It could be with a particular population, it could be with a set of students, or in the case of CRE, it would be in the case of a particular reaction carried out at a particular condition, set of conditions of pressure and temperature. So you determine how the concentration changes or how the volume changes and so on and so forth. So that's collecting experimental data. That way we can come up with the rate equation that will best shall I say, represent the behavior of the species or the species in your chemical reaction. Then after we have collected experimental data, we correlate this data by mathematical equation. So connected na sila actually. Your experimental data is useless. It does not have any use if you cannot come up with the correct equation. So that is mathematical equation or rate expression that will tell us how fast or how slow is the reactant being consumed or how fast is the product being produced. So collection has to be followed with correlation of this data with a rate equation. So without this data, we don't have any rate equation. Without the rate equation, you cannot design the reactor that will uh, facilitate the given reaction. So this is why it's included in here. So this is actually, by the way, these are actually in chronological order. So after you have the mathematical equation, you are now ready to design the suitable reactor that will facilitate the reaction. Then once you have the reactor, it doesn't end there because you need to specify the operating conditions. Is it constant volume? Is it constant pressure? Is it constant temperature? All those things. Will your reaction need to be housed in a chemical reactor that has some jacket for it to be heated or for it to be cooled in the process of reaction? All those things. So design the reactor specifying the operating conditions. So it could also include the auxiliary equipment, the design of the auxiliary equipment, and the methods of control. It could even include up to the point of what is the best type of reactor. Would it be plug flow? Will it be a constantly steered tank reactor, or would a simple batch reactor do? Actually, all reactions can be facilitated on a particular reactor. But question is, which is the best of the three? And if we say, let's say the best reactor is the constantly steered tank reactor, what's the best volume? What is the volume of the reactor that you need? How is it going to be operated? Is it to be operated with another CSTR to follow it, or a plug flow reactor will be better, something like that. So in the latter part of the course, you will be asked what is the best design. Put the CSTR before the plug flow or the plug flow before the CSTR. So you will only know that if you, of course, know how to quantify which of the two scenarios will give you a higher yield of the product or products. So all those things you will learn in CRE. And these are very, very important to us, especially to us chemical engineers, because we are chemical engineers. We're not just any engineers. So these are the things that we need to know. Now, since the core idea for chemical reaction engineering is kinetics and reactor design, so what is kinetics? I've mentioned them several times already in the course of the discussion. So it deals with how fast a reaction proceeds. So in here, we quantify reaction rates. It deals with mechanism of reaction, meaning taking into account the number of steps that are needed for the formation of the product or products, and deals with the effects of pressure, temperature, composition, and even the catalyst on reaction rates. We know that catalyst increases the rates of reaction. So they increase the rates of reaction. So the opposite of this, by the way, are the inhibitors. So how will it affect your production in that case if you have a catalyst, if you don't have a catalyst? Okay, these are the things that we need to that you will learn in kinetics. In reactor design, we start off with the very simple part of reactor design, which simply computes or calculates the size of the reactor based on the yield that is required in the problem. So given this yield, how big a reactor will you be needing? If you'll be needing a CSTR, how big would it be? If you'll be needing a PFR or a plug flow reactor, how big should it be? So these things are your initial requirements when you design reactors. Then we also deal with the type or the configuration of the reactor. When you speak of configuration, will it be best that I'll use this type, the batch reactor, or it's better that I use STR? No, it's best if I use PFR. All these things you will learn which of the three is best for a particular reaction. And configuration, meaning if you have several reactors in your system, so you have a system of reactor, what is the best combination? Should I have a PFR CSTR or a batch reactor followed by a PFR will do? Something like that. So that's configuration. Now, involves consideration of heat and mass transfer. This is towards the end when we quantify temperature effects in our reaction. So this part, the effect of heat and mass transfer in reactor design is normally given as a final requirement to students. So we'll see in your time now if we can have it as discussed based on your pacing. Okay, so this is reactor design and this is kinetics. Now, there is a mention here about the performance equation. There's a mention here about the performance equation for actually in reactor design already. So never mind, I can't find it here. So we have encountered that the two words performance equation. So the performance equation, from the term performance, it tells you how well your reactor performs in terms of the objective of producing the desired product or products. So your performance equation, simply put, relates the input to the output. Okay? In terms of the input, you have to add with it the contacting pattern, or how materials flow through and contact each other in the reactor. How early or late they mix. Are they clumpy or are they in the state of aggregation? So by their very nature, so there are some materials that are clumpy in the case of solids, and non-coalescing liquid droplets. So non-coalescing meaning there's no way that these liquid droplets will, shall I say, aggregate or close mix with another. So that's coalesce. They group together. So I think that's the most appropriate term. They're grouped together. So if we have this, these are all to be taken into consideration. How your raw material contact each other, raw materials rather, contact each other inside your reactor. And of course, the kinetics. Okay, these are all together with the input taken into consideration. That way we come up with the desired output. So again, kinetics here tells you of how are going to happen. So rate of reaction. If very fast, then equilibrium tells what will leave the reactor. So if the reaction is very fast, the state of equilibrium, meaning a balance already, meaning the rate of the forward and the reverse reactions are equal. So that tells you what will leave your reactor. Now, if not so fast, then the rate of reaction and maybe the heat and mass transfer will determine what will happen. So if it's not so fast, then it will be all about kinetics, and we need to consider also heat and mass transfer. Now, this is figure 1.2 in your textbook. So this is the information needed to predict what a reactor can do. And your performance equation relates this input or inputs, if I will include this two, to the output. So you have here, your output is a function of the input, the kinetics of reaction, and the contacting pattern, how your raw materials contact each other. Now, in a form of a table, Levenspiel gave us an overview, excuse me, on how well we can classify chemical reactions. Okay, so we can classify them based on the first column you're seeing here. So we can generally classify chemical reaction in terms of how many phase we see. So if it's homogeneous, we see only a single phase, and this is in the case of most liquid reactions. Okay, heterogeneous, then this is in the case of solid liquid reactions or solid gaseous reactions, especially in fixed bed reactors or fluidized bed reactors. So generally, this is how we classify them. But we can add the accounting of whether we have a catalyst present in our reaction. So it could be a non-catalytic reaction or a catalytic reaction. So most gas phase reactions are non-catalytic and homogeneous, and most liquid phase reactions, as I have mentioned before, are homogeneous. At the same time, they require the presence of a catalyst. That way your reaction can be optimized. Now, most non-catalytic reactions here, the burning of coal, they don't need catalysts. The roasting of ores, the attacks of solid by acids, gas liquid absorption with reaction. Gas liquid absorption is a unit operation, but when there is already a chemical reaction, then it's being studied under chemical reaction engineering already. And reduction of iron ore to iron and steel. These are heterogeneous in nature, and they don't require the presence of a catalyst. Otherwise, the next column here beside this one tells you that though they are heterogeneous by their but they require the presence of a catalyst. So the ammonia synthesis, the Haber process, the oxidation of ammonia to produce nitric acid, the cracking of crude oil, and the oxidation of sulfur dioxide to sulfur trioxide are examples of catalytic heterogeneous reactions. Something intermediate between homogeneous and heterogeneous are these fast reactions such as burning of a flame. We know that the burning of a flame is non-catalytic in nature. So it's something homogeneous and heterogeneous because at some point we see two reacting species, but at the latter part we only see one. So that is why it's intermediate between homogeneous and heterogeneous. It's the same thing with enzymatic and microbial reactions. So something intermediate between or something in the boundary of homogeneous and heterogeneous reactions. Enzymatic and microbial systems require the presence of a catalyst, just like reactions in colloidal systems or suspensions. Okay, so they are catalytic and something intermediate between homogeneous and heterogeneous reactions. Okay, so this example is the exact thing that you'll be seeing in your book by Octave Levenspiel. Now, if you're going to classify reactions in different ways as placed in your Perry's handbook, so in terms of mechanism, how many steps? Is it single step, double step? Is it irreversible? Is it reversible? Is it simultaneous? Or in the case of parallel competing reactions, is it consecutive? The usual idea that we have when we speak of mechanism, like step 1, step 2, step 3, so that's consecutive. But there are competing reactions or parallel reactions also. So this is how we classify reaction based on mechanism. The simplest of these four is the irreversible reaction. Now, it's a little bit complicated when we speak of, when we take into consideration already the reversibility of basically all reactions. It was discussed in your chemistry 1 that basically all reactions are reversible in nature. They just become irreversible when the rate of a particular, shall I say, direction, let's say be forward direction or reverse direction, dominates or is a lot greater than the other one. So that makes then your reversible reaction irreversible, because let's say the rate of one's direction is negligible compared to the other. But in reality, basically all uh, reactions have a certain degree of reversibility. Okay, so that is why they say basically all reactions are reversible. Now, in terms of molecularity, this considers the species that are needed to react to form the product or product. So unimolecular, you have a single species. Bimolecular, you have two from the term bi, prefix bi, and thermolecular when you have more than two. So it could be 3, 4, 5. So, but oftentimes we only deal with oftentimes with bimolecular reactions. But there are reactions that goes beyond having only two reacting species. Some may have even four species. Four species to come up with the desired product or products. Now, we can classify them based on operating conditions also. Now, this now more considers the design of the reactor, not just purely kinetics. We're not just simply looking into kinetics. So is it isothermal at constant pressure? Is it isothermal at constant volume? Or is it adiabatic? Or is it non-adiabatic and non-isothermal? So these reactors or reactions you will meet at the end, okay? Now, or it could be also classified based on equipment type or orientation. So I have mentioned this already. Are you using a stirred tank reactor? Are you using a tank battery, meaning several stirred tank reactors arranged in series? So that's what we mean with tank battery. Or are you simply using a single tubular reactor or plug flow reactor? Or are you using a multiple tubular reactor? Or is your reactor filled with solid particles that are inert or catalytic? They can either be inert or catalytic. So this is in the case of fixed bed reactors, moving bed reactors, and fluidized bed reactors. So these are classifications. The fourth classification of reaction based on equipment type and orientation. The last is how is your reactor operated, or the type of reaction that is. Is it batch? Is it something continuous or flowing? Or is it semi-batch? So this is the fifth way of classifying reactions. Now, as to variables that affect reaction rates, you know this in your Chem 1, that when a reaction is homogeneous, it's always temperature, pressure, and composition that we look into. So this is in the case of oftentimes most of the liquid reactions and gaseous reactions because they are homogeneous. So we look into the effect of temperature, pressure, and composition into the yield of the product or into the consumption of the reactants. If it's heterogeneous, aside from these three, the temperature, pressure, and composition, you look into heat and mass transfer. Also, you need to consider these two because they become rate controlling in the case of very fast reactions. Their effect will not be that, shall I say, felt by your system or that of great significance if the reaction is not fast or not very fast. But if it's very fast, you need to look or consider heat and mass transfer. Now, the next slide here is very important, and later in your, you have your dry lab later, so I will leave that to you. You read Octave Levenspiel and how these different ways of expressing rates of reaction associated with another, and how you're going to use, or how will you be able to identify the rate expression suitable for a given problem, because he gives also examples that have solutions on the use of these particular rate expressions. So the rate expression number one takes into account the phases that are present in your reaction. Do you have solids? Do you have liquid? Do you have a liquid? Do you have a gas phase reaction? So by that particular thing, you will know already what type of rate expression is suitable or appropriate for the given problem to you. So nobody can tell you that you use this particular rate equation. It's only you that can tell that to yourself that, okay, I'll use this particular rate equation because anyhow, my reaction is homogeneous, it's liquid, and I'm given the volume, so I will use this particular equation. You cannot use a rate equation that has solids that is used as a basis for it, because in the first place, your system does not have solids. Or something, what I'm trying to say, class, in here, do ka common sense na bala nga, hindi kaya magamit sa rate expression nga may solids, hindi kaya magamit sa rate equation nga talks about gases, because in the first place, you're given a liquid reaction. So you tell that you alone can, shall I say, decide or tell that to yourself, no, I'm not going to use the other forms of reaction equation because, or rate equations, because this is my system. So we'll go to these rate equations one by one. Actually, they can be equated to another by multiplying them by the basis or the denominator that appears in your rate expression. So this is the first one. Reaction rate is very important because there are problems that does not really require the chemical equation, meaning the stoichiometric equation A plus B forming C plus D. No, there are problems that are, shall I say, naturally observable and naturally observable phenomena that you don't need to be good in chemistry, or you don't need to have the chemical reaction for you to be able to solve it. All you just have to do is, based on these rate expressions, select which one is best for the problem that is given you. Meaning, the problem can be solved even if you don't know yet kinetics. It can be solved by simply the ideas that you learned in the past about dealing with units or dimensional analysis, as long as you are guided by the very important rate equation or reaction rate expression. Now, when we speak of reaction rate equation or reaction rate expression, I'd like to emphasize this. When you speak of a reaction rate expression, a reaction rate equation, we mean the differential equation. So when you speak of the differential equation, it has the presence of a derivative. Now, why am I stressing this one? Because later on, when you speak of kinetics, you will also be asked about the rate law. When we speak of the rate law, it does not have any derivative on it. It will only have the rate constant and the concentration terms. You will know that when we're there. But for now, we're talking about the reaction rate equation or the reaction rate expression. So mag-amo na siya gani, DE ang ginaistoryahan ta. So meaning, ang inyo formula dapat may derivative. As you could see here, these are all what you see on the left side, they are all written in the form of derivatives. When we speak of the reaction rate based on a unit volume of reacting fluid, notice that your divisor is V, meaning it's the volume. And your derivative is the rate of change of the number of moles of species I with respect to time, or simply the rate of change of the number of moles of I. As such, we write it as R sub I, meaning we're trying to present in an equation form how will species I react, okay, per unit volume of reacting fluid. So rate of change of the number of moles of I. So using this particular expression, derivative and volume here, it's based on unit volume. You could see the units are just simply following what you have written here on the left. So you have moles of I formed because this is moles of I. Volume of fluid, meaning the volume of the system, the reaction system, and of course the dt has to, of course, the time. So this rate, reaction rate, has the unit moles per unit volume per unit time. Where did I get it? I get it from this one. Okay? Based on unit volume of reacting fluid. What about if it's based on unit mass of the solid in a fluid-solid system? So in this case, now, it's specific that you have a fluid-solid system. Your fluid can either be in the form of a liquid or a gas. But what is very important is you know that you have a solid in your system. So it could be a gas solid or a liquid solid. If that is the case, class, you just change the volume divisor that you have in the common representation of the reaction rate to weight or the mass of the solid that is being used. And as such, your unit now will be your set of units rather will be moles of I per unit mass of solid per unit time. Okay? Now, what about the third one here? Based on unit interfacial surface. When will this be used in a two-fluid system? So you have a two-fluid system. So it could be liquid-liquid, gas-gas, or gas-liquid. Or based on the unit surface of solid in a gas-solid system. So this tells you that this formula is only for a gas-solid system. So what is the unit interfacial surface for this gas-solid system? Or it could be two fluid systems. So right away, the problem tells you what is given to you. So you can decide whether is this a two-fluid system or is this a gas-solid system. Am I given the interfacial surface in between my phases? So what I mean with phases, between my liquids between my gases, between my liquid and gas, or between my gas and solid. So then if that is the case, this will be the appropriate rate representation, rate equation. So you still have the rate of change of the moles of I, but this time you don't divide by volume. You don't divide by the mass of the solid, but you divide by the surface area, the interfacial surface in between your faces. So, tandaan kung ano ang faces, inyo siya applicable. So, these are the two faces that that are specific for this particular rate equation. Okay, we have two more here based on the unit volume of solid. So take note, the first one is unit volume of reacting fluid. This is in the case of liquid reactions. So this time, based on the unit volume of solid in a gas-solid system. So again, this rate expression is only applicable to gas-solid system. You still have the rate of change of the number of moles of I, but you divide by the volume of the solid in your gas-solid system. As such, your unit would be moles of I per unit volume of solid per unit time. Okay? Now, the last could be based on volume of reactor if, so there is an if different from the rate based on the unit volume of fluid. For example, class, you're given a system wherein the volume of the fluid or the liquid inside your reactor is different than the volume of the reactor itself. And the problem is asking you for the rate equation based on the volume of the reactor, not the volume of the system inside the reactor. If that is the case, then this is your appropriate rate expression. Okay, so still the rate of change of the number of moles, but you divide it by the volume of the reactor. Now, you may ask a question, how do we know, Miss, that we will divide by the volume of the reactor? Or we divide by simply the volume of the system inside the reactor. If the problem does not specify that your rate should be expressed in terms of the volume of the reactor, automatically it's referring to this one. And this is the usual case. You base the rate equation on the unit volume of the system of the fluid inside your reactor. Pero kung mag-specify gid siya reactor, then amo ni siya. Okay? Because it's not in all system class that your volume of reactor or your volume of your system is the same as the volume of the reactor. Oftentimes, that's the case. Hindi man pwede nga kung kinahanglan mo kung ang imo system, let's say for example, 1 cubic meter. Ang imo reactor 1 cubic meter man. When we design, we have shall I say, allowances for the volume of your reactor. So in that case, you just have to look for that particular phrase in the problem that specifies that you are to express the rate of your reaction based on the volume of the reactor. Otherwise, it's referring to the first one, the common way of expressing the rate of reaction. Okay? Now, though we have 5 different ways of expressing reaction rates, or we have 5 different reaction rate equations, depending on the type of problem that is given, all these 5 can be equated to each other since their common denominator is this rate of change of the number of moles of I. You can see this. They have all d and I dt. All you have to do is multiply it with the basis that was used in expressing the rate of reaction. So in the case of Ri, you multiply it with the volume of fluid, it's now dNI dt. In the case of Ri prime, this one, you multiply it with the weight of the solid. In the case of Ri double prime, you multiply it with the surface area of the interfacial surface between your faces. In the case of Ri triple prime, you multiply it with the volume of the solid for your gas solid system. In the case of R to the fourth prime, then that would be simply multiplying it with the volume of the reactor. They are all equal, All these expressions are equal because they represent d and I dt. Do you get it? Do you have any questions so far? Okay, so I think your silence means that you follow through. So the reaction rate, this one, this reaction rates, expressions or equations, is the rate at which a species, referring to your reactant, loses its chemical identity per unit volume of your system. The rate of a reaction can be expressed as the rate of disappearance of the reactant or the rate of appearance of a product. Now, speaking of this class, the rate of disappearance. How will you distinguish a rate expression giving you the rate of disappearance and a rate expression or a rate equation that gives you the rate of formation or the rate of appearance of a product? Very simple. We go back here. If all of these are positive, you see these are Ri prime, Ri double prime, Ri triple prime, and so on. They are all positive, right? This one tells you that this rate, reaction rate, is for a product I. Why? Because it's positive. This reaction rate represents the rate of appearance of formation of species I, which is a product. Once you see a negative sign here, negative di siya, that tells you that the rate equation that is provided to you is for species I, which is a reactant. It's disappearing. And as such, the rate expression as written is negative. But when it is positive, then your species is a product. So speaking of this bullet here. So the rate of reaction oftentimes class, like most of the time, but not all the time, is always expressed in terms of the rate of disappearance of the reactant or of the species. That way, they can be converted into the product. But there are rates of reactions that are expressed in terms of formation of the product or appearance of the product. So that makes it positive. So that is why in the first bullet here, class, so ang specify agad ang species that loses its identity. So it's referring to the reactant that loses or reduces its amount because it is being converted now into the product. Now, since it's time already, I want you to read this. It has anyway, the solution is there anyway, and it's very self-explanatory. Now, these sample problems are sample problems found in your book by Levenspiel. It has also solution there. So for your activity this afternoon, you will have to read this portion in Levenspiel and study the solution of these two, because I will not anymore do into explanation, because when I was a student there, and even in face-to-face scenario, I don't explain this anymore. So I let the student study, and next week, when we see each other, you can raise concerns regarding what you have read in here. You will have an assignment related to these two. It's based on the solution that is provided by Levenspiel. It's a text assignment, so all you have to do is write your answer to the questions, and it's due later 11:59 p.m. So to make sure that you study these two problems. But still, you can we can have feedbacking on this next meeting, that's next week, as to any part that is not clear to you, should there be any. Okay? Now, I'm done for today's lesson. Do you have any questions or clarification? And your assignment, by the way, since it's an assignment, it's not a problem set, then it has to be accomplished individually. You have no questions, class?
None, miss.
Sige, sige. Okay, so if you don't have any more questions, this is it for this is for us for this week only. So next week we'll continue with kinetics. So hopefully ang wala di subong ara sila next week. Okay? Sige. Take care everyone. I'll see you again next week, Monday. Bye for now.
Thank you, Miss.